I want to really dedicate this to the CMS collaboration. It's a fantastic collaboration. This is a picture we took last week. We had a party. This is only 400 or 500 people. Remember, there are 4,000 people in the experiment. This is not the real CMS detector. That's down underground. This is the spare that we keep upstairs. Okay. So, one page for the theorist. That's all they deserve. No, I'm kidding. The standard model is here. Is shown here. This is what we know. These are the particles making up the standard model that we've known and seen up till now. The amazing thing is that it's been tested for years and years at LEP and so forth. And we have now confirmed it to better than 1% in really hundreds of measurements. It's getting really quite annoying. But very impressive. I mean, it's just amazing. But there's one piece that's missing, and that's what we call the Higgs. And that's what we're going to talk about today. And so this is where things stood last week. Let's see if this works. Yeah, okay. This is where we stood last week. As you know, if you look at the radiative corrections to the W, there's a connection to the top, goes like the top squared, to the Higgs that goes like the log. So if you know the W and top mass very well, you can actually predict along bands where you would find the Higgs. And there were two major developments last year. One at the Tevatron, they really had a tour de force measurement of the W mass down to 15 MeV, which is just astounding for a hadron collider. And that shrunk this ellipse. I'm kind of nervous for some reason, I'm not sure. Shrunk this ellipse down to this green one. And then the colliders, this whole space here was gray. And you can see we basically eliminated a 475 JeV band of possibilities. And we were down to spot. And you see they nicely intersect there. And that's a good place to look. And that's what the rest of this talk will be about. Now we moved to ATeV this year. So here's the cross-section. For production of standard model Higgs. Mainly it's direct production via gluon fusion through a top quark loop. But there are many other ways it can be produced. One that's very important is vector boson fusion, and that will come into play here. But in fact, all of the four main modes are exploited in our searches, including TTH, which I'll show only very briefly, but it will be discussed more at ICHEP. And an important thing about the 8TeV is that we gained relative to 7TeV last year by about 25 to 30% in the rate of production of Higgs at low mass. So this is very important, and you see that in the data and the results. Actually, I can use this thing. So where do we look? We in this talk, I'll talk about 5 decay modes. These are the branching ratios of the Higgs. If you're at high mass, it's mainly vector bosons. But we're looking in this little range that I told you about, and it's a very interesting range because it has a rich array of decays. So it's fantastic from the physics standpoint. From the experimental standpoint of trying to find this, it makes life harder. Because you have many things that it's splitting to, and you have to try to dig them all out. So for the low mass searches, which I'll concentrate on today, we look for BB bar, tau tau, WW, ZZ, and 2 photons. And we get very good mass resolution in these two channels. So, the region that's not yet excluded is about 115 to 130, let's say. I mentioned the 5 decay modes, and this shows our sensitivity to setting limits or excluding the standard model in these 5 modes. And you can see in this range, we're actually fairly comparable across all of them, within a factor of 2 or so. They're very, very strong now, these modes. And then this combines them, and so the one thing you know, of course you have no idea what I'm going to say at the conclusion, I know, but the one thing you know for sure is that we are in a position to exclude the standard model at this point. Looked at it another way, you can ask what's the discovery potential. Now the probability that the background would fluctuate up to a given signal the size of the standard model, given where we are now, is shown for the 5 channels here, and this is the sum. So in this range, we'd expect somewhere between 5 and 6 standard deviations excess if there was a standard model Higgs. And we'd have excellent opportunities, we hope, with more data to really study this thing. Okay, how did we get here so fast? One of the key ingredients was the LHC. I want to thank Steve and all of the people involved, Lynn, who put this amazing machine together and ran it. You can see this is the 2010 run down here. That's not a mistake. That's actually the first year of running. It was there last year, and then this is the rocket we're on right now in 2012. So in this talk, we use about 5.2 inverse femtobarns from 2012. And this 5.2 inverse femtobarns is perfect. So we collected actually 6.7. We're still working on gathering more data. It takes some time to certify data that has slight problems, but already 5.2 is golden. 5.6 is good for any kind of a muon analysis as well. And so those are the samples we use this year. Last year they're just slightly smaller in size, but they're at 7 TeV. This is CMS. I can't spend a lot of time. I could spend hours on this, but there's some key things about CMS. This is a detector, I think, that has built on many generations of experience. From the Tevatron, we learned that silicon works well in tracking, and we gambled in CMS and built an all-silicon tracker. That's 200 square meters of silicon, almost 10 million channels. Inside of that, there's a 66 million channel pixel detector. Outside that, we have all of our calorimetry inside of this amazing magnet, which is 3.8 Tesla. It's huge. Huge stored energy, holds the entire tracking system in calorimetry, and gives us a fantastic effect in terms of being able to spread out all the particles coming out from the interaction. And this is effectively increasing your granularity, which is already very, very high in CMS. And that gives us a lot of power, and we're still learning what this detector can do. And it's still surprising us, I think, to some extent. The hadron calorimeter is brass scintillator. And works very well, but the really exceptional thing is the electromagnetic calorimeter, which is another first for a hadron collider. It's made of lead tungstate crystals, about 75,000 crystals. Each is about 30 centimeters long, 2.5 centimeters around. So in principle, the Molière radius is really within one of these crystals. You should be able to capture an electron. Of course, electrons won't hit dead-on center face. So typically, an unconverted photon will be contained in 9 crystals, the one surrounding the hit and the one that is hit. And these are all crucial to our results I'll show today. I'm going to run over, Rolf. No, I'll try to pick up the pace. And then we have these muon detectors, which are very, very nice on the outside, completely hermetic and redundant. All right, everything's working great. I'm going to pick up the pace. This is 100%. You see, everything's working very well, close to 100%. And this is amazing after 3 years of running that we can keep things going this well. It's taking more effort. People are getting tired, but it's going well. Now, the ecal is crucial to several of our measurements, Higgs 2 photons, all the electrons in ZZ and so forth. So I wanted to show you briefly some of the things we do. We use many low-energy, etas, pi's, and so forth to get the low-end calibration, intercalibration. We also use W events. But with radiation, you see our response is falling. The radiation damage, the crystals are becoming less transparent. We monitor these with lasers. We have to do a correction that involves modeling how light propagates in the crystals. That's applied. That's the blue line. And you see it brings us up to here. So in WE new events, we actually have a 0.2% stability across the run. This takes a tremendous amount of effort and a lot of people involved, but it's done very well. And then we get very good resolution, as you can see here, at the percent level. Moving on, I just want to give another reason we got here is that last year we found, I don't have time to explain this slide in detail, but what we found, if you just listen to the words, is that with this high pileup of many interactions, the processing time per event went up dramatically, and we would not have been able to run this year very well. So our computing guys and many of the people in physics dug in and found a factor of 2.5, in speed, so that we were under about 15 seconds per event. And we were able to do this without changing any of the cuts, without actually having any cuts on tracking or anything. So that got us in very good position to take data this year. And our Monte Carlos. We produce about 400 million at generator level per month. That's a huge number, and 1 billion per month that are jigged and reconstructed. So that's part of the reason we were able to show results this quickly. Okay, in terms of reconstruction, using the high granularity of the detector, we have what we call a global event description, or what was called before particle flow. It's based on particle flow. And the basic concept is you start with real physics, generally just basic particles. They get manifested in various ways in your detector. We combine all that information. We return a list of reconstructed particles and basically reconstruct something very close to the original underlying interaction, the real interaction itself. And that allows us to do a fantastic job of doing the physics. Everything can be done from this list of particles, and it eliminates redundancy, simplifies isolation, and so forth. And you'll see some of the effects of that. For electrons, we have very sophisticated electron reconstruction in the eCal. We take into account, using Gaussian sum filters, the energy lost due to Bremsstrahlung. As you know, that's a stochastic effect. You can't just use a simple Gaussian. You have to actually mix Gaussians, and that's what's done in this. And that allows us to track out to right out to the eCal. And we have very specific photon identification, and for energy scale and resolution, we use Z's and J size to electrons, and we also study photons with Z's. And you can see then the comparison of data in Monte Carlo in the barrel is excellent. And we have about a 1.2 GeV resolution. For electron identification, we use multivariate techniques. We feed a lot of information, and we found a 30% improvement, in fact, in H to Z, Z to 4E this year. This has gotten us some improvement. And you can see the kind of separation we're getting between electrons from Z's. And these are actually additional jets in Z events that pass loose lepton requirements. And you see they fail our multivariate. And you see our working points here. This is signal efficiency versus background efficiency. This is where we were in 2012 for low PT, and now we're up here. And for high PT, we're up here. So we're gaining everywhere in sensitivity. I have to move more quickly. I'll just say that for muons, we also have particle flow muons. We get really high efficiency down to 5 GeV. Fantastic efficiency above 10 GeV. You can see this studying this J size. Remarkable how flat our efficiency is and how high. And this is the more remarkable thing, that there's completely no dependence on the number of interactions. And this has been taken out in the last few months. For isolation, we do something fairly sophisticated. I'll get into it later. But we sum the energy of the particle flow particles basically in rings around the main particle. And again, we see that the efficiency of the isolation cut is completely flat. You can see now also here, this is for muons. You see for electrons how much better we're doing. This is efficiency. You can't see it. This is background. And we've gone from here to here. So we're higher efficiency with lower fake rates. Tau identification is very sophisticated. We actually reconstruct 1, 2, and 3 prong. We can reconstruct rows and A's, and we get incredibly high efficiency, as high as 70%, with a very low fake rate. And again, we use these for isolation. We use energy deposits in rings and feed that to a multivariate discriminator. For jets, we were quite worried at the beginning of the year. The pileup adds lots of jets, and that changes your jet counting, which affects your categories for the different different Higgs searches. And what we've learned is that we can compensate by knowing, of course, what tracks are tracked from the tracker, where they are coming from what vertex. But even outside the tracker, we can see the jet shape is different. Typical pileup jets are often overlaps of just several different particles, and the structure is different. And so you can see this is the ratio of jets to the fraction of events with 0 jets in various bins of multi-interactions, and they all lie on top of each other. And here's the ratio with the lowest multi-interaction bin, and you see there's a couple of % spread here, and then almost nothing. So we've eliminated the impact of pileup, basically, which I find just astounding. And with this kind of thing, and in general, this is 2011 plots. I didn't have time to get the new ones, but I wanted to say that we have fantastic jet resolution. This shows you jet PTs out to 1 or 2 TeV, within 15% of expectation at next to leading order, and a magnificent Drell-Yan spectrum, again, bang on, all the way out to 1.5 TeV. So, in summary, we understand, I didn't talk about top, but we understand top. We've got the top mass and reconstruction coming in very well, cross-section, and we've slowly, as we've gathered data, rediscovered the standard model to more and more rare processes, and basically we're very confident now that we can go after the rarest, which is the Higgs.